So we've had some announcements, and now it's time to continue the morning session. Andy Lewis will be talking about the typical Turing degree.
Okay, so thanks first to the organisers for inviting me. So I'm going to be talking about some work that I did with George and Adam last year, and which is aimed at characterising the typical Turing degree. Okay, so the aim is to establish which properties are satisfied by the typical Turing degree. So it may or may not be immediately obvious what I mean by typical, okay? But basically typicality can be gauged either in terms of measure or in terms of category, and we're interested in both of those cases. And in particular, we're interested in comparing what happens when you think in terms of measure and when you think in terms of category. Okay. So my route into this area basically came via this question of Carl Jokic. So I was at a meeting in Notre Dame, and he asked me this question, which apparently he's asked a number of times before. So what is the measure of the degrees which satisfy the coupling property? Okay, so let's make sure that this is completely clear. So the measure we're considering is a standard Lebesgue measure, right? The measure of a set of degrees is just the measure of the union, right? So the measure of the set of all reals in those degrees. So it's a classic result of Sachs that says the minimal degrees are of measure 0, so it just means the set of all reals of minimal degree is of measure 0. And then the cupping property is a very simple thing. It just means you can be non-trivially cupped up to all degrees above. Okay, so A satisfies the cupping property means that for all B above A, there exists some C strictly below B, A joins C equals B. Okay. So I went away and thought about this for a while and talked to George about it, and we realized that we could answer this question. So the answer is 0. Okay, so if you think in a measure theoretic sort of way, then the typical degree doesn't satisfy cupping. And then, so George asked a question which in retrospect was entirely obvious, but which I hadn't thought of. Okay, so we know the measure is 0, but then what is the level of randomness required in order to ensure that you don't satisfy cupping? The point here being that if a set is null, then it's effectively null relative to some oracle, right? Set being null just means it has arbitrarily small open coverings. So obviously some oracle will be able to enumerate those coverings. So if you're null, then you're effectively null relative to some oracle. So in other words, if a set is a measure 0, then there's some level of randomness, some oracle A such as a random relative way, then you can't belong to the set. Or the other way around, so if a set is a measure 1, then there's some level of randomness that suffices to ensure that you do belong to the set. Okay, so we thought about that, we can answer that too. So 2 randomness is suffices, and that sharp 1 randomness doesn't suffice. Okay, so then this seems like a sort of quite a nice sort of fact, right? So you've got this classic result of Sachs that the minimal degrees are of measure 0. That was actually, so that was extended by Jeff Paris, who showed that the degrees which are bound of minimal, they're also of measure 0. And now you have another result along those lines. So this kind of suggests an obvious program of research, right? Why not consider other properties? So initially, maybe we want to restrict to definable properties. So by definable, I mean definable as a subset of the structure, right? So in the language of partial orders. So the idea is that for each definable property, we want to establish, does the typical degree satisfy the property, or does it satisfy the negation? And then how random do you have to be in order to be typical? Okay, so we started working on this stuff, and then we found out that Adam was interested in some of the same questions, so we joined forces. Okay, so let's just briefly take a step back from that then. So I said that for each definable property, you want to establish, does the typical degree satisfy the property, or does it satisfy the negation? But why must one of those two possibilities hold, right? Why couldn't it be that it's half and half? So that basically just follows directly from Kolmogorov-Zirawan law. So this tells us that every measurable tail set is either of measure 0 or measure 1. So just in case people aren't familiar, which I guess they will be, P is a tail set, so P is a set of infinite binary strings. A tail set means that for any finite string sigma and the infinite string A, this is an A, even only if, sorry, is in P, even only if A is in P. I don't know if you can see that over there. Okay. So basically you can add on or take away any finite initial segment, doesn't change whether or not you belong to the set. So measurable tail sets are either measure 0 or measure 1. That's a very simple proof. So if P is a tail set, so let's suppose P is a tail set, and let's suppose that W specifies an open covering of P. Okay, so W is a set of finite binary strings. Square brackets W is all the infinite strings extending some end of W, of So P is a tail set, W gives an open covering, and let's suppose that W is of measure alpha, set given by W is of measure alpha. Then we can form this other set W star in a simple way. This is because I said all strings sigma concatenated with tau, such that sigma and tau are both in W. Okay, so you can think of that the following way. Each sigma in W, right, we're replacing everything above sigma like another copy of W above there. So if you look at it in that way, it's kind of obvious that the measure of this new set is now alpha squared. Okay? But because this P is a tail set, it still gives you an open covering. So what have we established there? So we haven't really used the measurability directly in any way yet, right? What we've basically shown is if you're a tail set, you're of outer measure 0 or outer measure 1. So that leaves the possibility that you're of outer measure 1 and your complement's of outer measure 1. And that's possible. Okay, that's a result due to Rosenthal. So, okay, anyway, so we get what we want, right? Because Turing degrees are clearly tail sets. So for every measurable set of Turing degrees is either measure 0 or measure 1. So any property that we consider, so long as the satisfying class is measurable, then so either the typical degree must satisfy the property or the typical degree must satisfy the negation. Okay, so that's the measure side of things. So let's just briefly look at the category side of things, right? So set as meager is a countable union of nowhere dense sets, and the set being co-meager is sort of as being some sort of indication that it's large. And then there's a nice characterization of the meager and co-meager tail sets, which is given in terms of Banach-Mazur games. So they work as follows. Okay, so first of all, you specify your underlying set P. We're going to suppose P is a tail set. It makes it a little bit simpler. We only care about tail sets. You've got two players, player 1 and player 2. So player 1 wants to end up outside P, player 2 wants to end up inside P, and they take it in turn. So player 1 chooses some string, player 2 chooses any extension of that, player 1 chooses any extension of that, and so on. And at the end of the game, player 1 wins if you end up outside P, and player 2 wins if you end up inside P. And what you find is that player 1 has a winning strategy even only if it's meager, and player 2 has a winning strategy even only if it's co-meager. Okay, so the basic idea here is that we want to do exactly the same sort of, analog of what we were doing for the measure case, right? So for each definable property, we can ask, well, is the satisfying class meager or co-meager? So we think in terms of category. Does the typical degree satisfy the property or the negation? And then the role that was played by randomness in the context of measure is now played by genericity, the standard form of genericity that we're used to dealing with when we talk about 1 generics, 2 generics, and so on. Okay. And this works exactly the same way. So if the set is co-meager, then there's going to be some level of genericity that suffices to ensure that you belong to the set. Okay, so that's our basic sort of setup. So what we want to do now is to just start considering properties, right, to see which way they go. So we want to, the properties we're going to consider are the sort of simplest properties for which it's interesting. And for each property, we want to think, if we think in terms of measure, if we think in terms of category, does the typical degree satisfy the property? And then how random or how generic do you have to be in order to be typical? So let's start right at the beginning. So I talked about the minimal case a little bit already. So it's a very simple property, the property being a minimal degree. Okay, and this was already answered by Sachs. So Sachs told us, okay, the typical degree, if you think in terms of measure, is not minimal. And then we can ask, so how random do you have to be? And then again, that's easy. It's easy to see that if you're one random, you're already not minimal. Right, there is one random, write it in the form BO plus C, and they have to be Turing incomparable. Okay, so the measure case is easy, and actually so the category case goes exactly the same way. So the minimal degree is meager, shown by Myhill, and in fact one genericity suffices. Well, exactly the same proof. Right? If A is one generic, write it in the form BO plus C, they have to be incomparable. Okay, so that was easy, so let's go to a property that's a little bit more complicated to deal with. So bounding a minimal. So first of all, a little bit of background. So what do we know about degrees which bound minimals even before we start thinking in terms of measure and category and stuff? Well, so Barry showed that all high degrees below 0 prime bound minimal degrees. And that was extended by Karl Jokusch, who showed that all generalized high degrees bound minimal degrees. I haven't written the definition of the generalized jump hierarchy down. I don't know if I need to do that. Okay, so basically being generalized high means that your nth jump is as high as it possibly could be in comparison with this join with 0 prime. And being generalized low means that your nth jump is as low as it possibly could be in comparison with the join with 0 prime. So generally speaking, being generalized high, in terms of the sort of the definable properties that you satisfy, seems to be very similar to being sort of like below 0 prime and being high. So being generalized high n is like being high n and below 0 prime, I guess. And being generalized low n is kind of like being low n and below 0 prime. Okay. Right, so if you're reasonably high up, then your bound minimal degrees, actually you can extend that. If you're reasonably high up, then you're actually the join of two minimal degrees. Okay, so then what happens when we think in terms of measure? So this was answered by Jeff Paris in 1972 or so. So he showed that the typical degree doesn't bound a minimal degree. Okay, maybe it's interesting to place that in a little bit of context. So Paris wrote that paper in response to a question asked by Martin in his 1960 paper, unpublished paper. So Martin asked precisely that question. So what is the measure of the degrees which bound minimal degrees? And in the 1960 paper, Martin was basically putting forward the idea that measure and category arguments might be used in order to sort of provide an alternative to direct constructions. So, for example, he showed the following thing. So the Turing upwards closure of a meager set of degrees that is downwards closed amongst non-zero degrees but doesn't contain 0 is meager. Okay, so you take a meager set of degrees which is downwards closed but not 0, not including 0, then this will still be meager when you take the upwards closure. So that has some immediate consequences, right? So in particular, the minimal degrees satisfy this property, right? They're meager, they satisfy this downwards closure property. So that says that the upwards closure is still meager, and in particular, then there are degrees which don't bound minimal degrees. So that's a nice example of that sort of idea. But then in this respect, perhaps Paris's paper was a bit disappointing, basically because it was very complicated. So it kind of made it clear that measure arguments weren't necessarily going to provide like a simple alternative to direct construction. Okay, so where are we? So we know that the degrees which bound minimals, the typical degree doesn't bound minimal degrees. And that was extended by Kurtz a little bit later. So he showed that actually, for almost all degrees of what measures 0, non-zero degrees below bound 1 generics. Right, we already said 1 generics aren't minimal. So that's a strictly stronger result. But from neither of those proofs is it obvious the level of randomness required. Okay? So we'll be able to answer that. So in fact, 2 randomness is well, first of all, 2 randomness suffices. So if you're 2 random, they're non-zero below, you bound to 1 generic. So 2 randoms don't bound minimal degrees. Okay, so it's clear then that 2 randomness suffices, 1 randomness doesn't. Right, certainly, so 0 prime is 1 random and does bound minimal degrees. Right, that's Sachs's result. But now we want to see precisely how sharp that is. Okay, so let's consider some notions in between 1 randomness and 2 randomness. So we consider weakly 2 random and Demuth random. So weakly 2 random, it doesn't belong to any null pi 0 2 class, and then Demuth random. Andre talked about at length over the week. So here's the definition of the Demuth test. So it's just like a Martin-Loft test, except that now this function which specifies the indices doesn't have to be computable, just WTT reduced to the whole thing result. Okay, so you have a computably bounded number of mining changes. And then you fail the test if you belong to infinitely many of the VM. So you have 1 randomness, 2 randomness. These are 2 notions that are incomparable, okay, and strictly in between 1 randomness and 2 randomness. So let's see what happens here. Okay, so first of all, let's deal with the Demuth randoms. So this case is basically, you have Demuth randoms which are delta 2. Then you can use Kuchera's fixed point free permitting, delta 2 stuff. It will bound a CE, and every CE bounds a minimal. Okay, so you do have Demuth randoms bounding minimal. And then how do we deal with the weakly 2 random case? So that's done in an entirely different way. It has to be, right? So we do that by showing you can have weakly 2 randoms which are generalized high. Okay, so all 2 randoms are generalized low, but you can have weakly 2 randoms that are generalized high. and all generalized high degrees bound minimal degrees. Right? I said that on the first slide. So that settles that. Okay, so that's the measure side of things. So let's look at the category side. So I mentioned this a little bit already. So Martin gave the answer. He said that most degrees don't bound minimals when you think in terms of category. And then, so 2 genericity suffices and 1 genericity doesn't suffice. Okay, you have 1 generics which bound minimal degrees, as well as obviously 1 generics that don't bound minimal degrees. Okay, so here's a sort of rough summary of what we've established so far, okay? So I'm missing some of the results out, but basically what's happened so far is it's gone the same for measure and for category, right? Because instead of being a minimal degree, bounding a minimal degree, it went the same way in both cases, and even the levels required were the same. So 1 randomness sufficed and 1 genericity sufficed in the first case, and in the second case, bounding minimals, it was 2 randomness and 2 genericity, right? And they've gone exactly the same way. So now let's look at a third property. Let's consider the join property. Okay, so this is a simple definition. Just means all non-zero degrees below can be non-trivially joined up by a degree below you. So a little bit of background first of all. So a bunch of us showed that all non-GL2 degrees satisfy the join property. But that leaves potentially quite a messy picture. So the degrees that satisfy join, they're not upwards closed. The non-GL2 degrees are not upwards closed. Right? If you're generalized high and you're not above 0 prime, you have a generalized low above you. So potentially outside, so everything above 0 prime will satisfy join, but out to the side it can be very messy. Okay, and then so what happens when you look at the measure case? Well, most degrees do satisfy join. Okay, and 2 randomness suffices. So when you think in terms of measure, the typical degree does satisfy the join property. Okay, and that's sharp in the sense that 1 randomness doesn't suffice. So why is that? Well, this follows from the fact that all low fixed point free degrees fail to satisfy the join property. Okay, so by low basis theorem you have low randoms, right, and they're fixed point free, so they'll fail to satisfy join. And the same result then works for Demuth randoms. Right, but the case for weakly 2 random is open. I'm not sure how hard we tried to solve that. I don't know if it's difficult or not. I'm not sure. Okay, so all 2 random satisfy join, and in fact we're able to strengthen that to show that everything non-zero below a 2 random satisfies join, or in fact everything below 2 random satisfies join. The way I gave the definition, 0 prime trivially satisfies join. Okay. So that's the measure side of things. So let's look at the category side. Okay, so well, this goes the same way, but now the levels required are slightly different. Okay, so Docker showed that the typical degree does satisfy join when you think in terms of category. And in fact, all 2 generic degrees satisfy the join property. But he didn't really prove that by thinking in terms of join, he proved it by thinking in terms of the cupping property. So actually what he showed was that all 2 generics satisfy the cupping property. And then there's this result that if you're n generic, any non-zero below you bounds an n generic. Right? So if you're 2 generic, any non-zero below you will bound a 2 generic. If he satisfies cupping, well, the cupping property is upwards closed, which means that this degree satisfies cupping, because they can be cupped up. Okay, so it's all done by the fact that they satisfy the cupping property. So that proof definitely requires 2 genericity. It won't work for 1 genericity, because 1 generics don't necessarily satisfy cupping. So you might sort of think, okay, that must be the level required. Yeah? But in fact, if you go via a completely different proof, you realize that's not true. So in fact, 1 generics already satisfy the join property, proving it a different way. Okay, so now I want to make a sort of observation, which is that for all the properties we've considered so far, whenever we've been able to show like a sufficiently random or sufficiently generic degree satisfies a property, we've also been able to show that's true for all non-zero degrees below. Right? So we showed it for minimality, for sufficiently random or sufficiently generic, not minimal. But that's also true for non-zero degrees below. And it also works. So if you're sufficiently random or sufficiently generic, then you bound a 1 generic. That's also true for non-zero degrees below. And again, for the join property. So sufficiently random, sufficiently generic, you satisfy join, and so do all non-zero degrees below. So let's isolate this as a potentially interesting principle and sort of investigate the extent to which it holds. Okay? So the idea is, if you take any natural definable property satisfied by all sufficiently random or generic degrees, then it's likely to be satisfied by all non-zero degrees below as well. So the reason for believing that is what? Well, basically, so it works for the properties I've talked about already. It'll work for the properties I'm going to talk about. And then the second reason, I'm not sure how much of a reason this is, but the second possible reason is that we've developed sort of two frameworks working on this kind of stuff. So there's one very simple framework, which is used for showing that all sufficiently random degrees satisfy a property. And then another framework, a more complicated framework, for showing that all non-zero degrees below a sufficiently random degree satisfy a property. But basically, if you've got a proof using the first framework, it's kind of obvious how to translate it into a proof in the second framework. Okay? So basically, if you're using our methods, then this principle is likely to hold. And maybe that's why we've come up with this principle. Okay, so what I'm going to do now is to describe a little bit about the simpler framework. The one for showing that all sufficiently random degrees satisfy a certain property. Okay? As I sort of go to describe the framework, I'm going to try and illustrate it with the simplest possible example, which is showing that all sufficiently random degrees bound are one generic. Okay? That's a very simple example, so hopefully it makes things fairly clear. Okay, so what is it we want to do here? So we've got a property, and we want to show that the property holds for almost all degrees. Right? So in fact, what we're going to do is we're going to assume we're given some number k, and we want to show that it holds for all but measure at most 2 to the minus k. Right? We can do that uniformly in k, and we'll be done. So we're given k, we want to make sure it holds for measure, the property holds for measure all but at most 2 to the minus k. And in order to do that, we're going to work for all sets simultaneously. Right? So we're working for all sets simultaneously, but the construction is going to fail for a small number of the sets. Okay, so to define the construction, there are basically 3 basic steps. So the first one's not very surprising. It basically just says, well, write out your list of requirements. Okay. So we're working for all sets x. So you write out a list of requirements that you want each given x to satisfy, and you're aware that you're going to fail for some. Okay, so that's step 1. And then step 2 says we have to devise an atomic strategy, an atomic module, which will work above any given string tau, and which will look to satisfy, say, the reth requirement on the extensions of tau, and which must succeed for a fixed proportion of those strings. It doesn't have to be a large proportion, but it should be a fixed proportion, which could depend upon e, but it can't depend upon tau. Okay, so you have to define a module or strategy which will work above any given string tau, and work to satisfy the reth requirement, and which will succeed for a fixed proportion of the strings. And that fixed proportion can depend upon e, but not upon tau. Okay, and then obviously we have to assemble these atomic strategies, these atomic modules in a standard way. I'll say a little bit more about that. Okay, so let's see this in terms of the example. So these first 3 steps in terms of the example. So we want to show that all sufficiently random degrees, or most degrees, bound a 1 generic. Okay, so the requirements then, so what we want to do is we want to work for all sets x, and we're defining a Turing functional phi, and for almost all of them we want phi of x to be 1 generic. Yep. So the requirements are just obvious, they're just our 1 genericity requirements. We want phi of x to be 1 generic. So that's the first step, and the second step is that we want to devise this atomic module, right? It has to work above a given string tau and satisfy the requirement for a fixed proportion of the strings. In this case, it's almost sort of trivial, because the module working above tau works as follows. It just reserves a sort of small measure of the strings, so a measure that depends just on e. K is fixed at the construction, it just depends on e. And it says, okay, we're going to freeze the construction above here. Above here, you stop enumerating axioms for phi. And then it waits to see whether or not any string enters WE descending via tau. And if it does, then we've succeeded for this string. Right? Then we can map phi to that string. We're satisfied for that requirement for that string. So either nothing enters WE appropriate, in which case we satisfy the requirement for a large proportion of the strings, or even if it does, we still satisfy it for this fixed proportion. Yep. So it's a very simple module. Yep. Okay. So that's the first two steps in terms of the example. And then basically we've got to specify the last step, right? So we've got to specify how do you put these modules together. So the framework won't tell you like exactly how to put the modules together in each case, but there are some basic rules you want to satisfy, and they're kind of fairly obvious. So, right, so the basic system involves putting down markers, right? If I put an E marker, that means if I put an E marker on a string tau, that means you immediately start running the module which works to satisfy the ETH requirement above tau, right? And which must succeed for a fixed proportion. Okay? So if I put an E marker on tau, that means you immediately start running the module which looks to satisfy the ETH requirement on the strings extending tau, which you've already described. Okay, so the basic rules are as follows. At most, one marker sits on any string at any given stage. Okay, fine. If I place a D marker on some string tau and an E marker on some extension, then E must be greater than or equal to D, so you'll place them in order. Okay. And then we're also allowed to remove markers from strings at any given stage. And the last one there just says, okay, if I remove a marker from a string, then I remove all markers from extensions of those strings as well. So let's see in terms of the example. Right? So how would we, if we're bounding a one generic? Well, what we do is we start off at the empty string, and you just place a 0 marker here, and then that module says to reserve a certain amount of the measure. So we don't place a 1 marker on the reserved measure, but on all other strings at length we place 1 markers. And then above them we proceed in a similar way, right? So above them you're going to reserve a certain amount of the measure and put 2 markers, and so on, blah, 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 blah. And you're waiting for a string to enter W0, and when that happens, well, now you've succeeded for this string. So you place a 1 marker here. You have to remove all the markers you've placed on strings above here, because now we thought we'd satisfied the 0 requirement for these strings, but we haven't anymore, so we've got to try again. So now on strings of some long length, we'll put, for all of those strings, we'll put 0 markers, and we'll try again. Okay, so that completely specifies the construction. Okay, so now let's just look at the verification, right? Let's look at the various different possible outcomes. So the outcome of the construction with respect to a particular real is given by the permanent markers that are placed on initial segments. And there are 3 different possibilities. So the first possibility is the good one, just that we permanently place an E marker on every initial segment of X. In that case, we get to satisfy all requirements, so we're happy. The second possibility is a problematic one. It could be that there's some least E so that we place infinitely many permanent E markers on initial segments of X. Right, so we look in terms of the example. So here we placed a 0 marker, and we waited to see whether something was enumerated into W0. When it was, we had to remove all these markers from these strings, right? And the strings of long length, we place 0 markers again. But that could happen again and again and again, right? So certainly for some reals X, you could get infinitely many 0 markers being placed and permanent 0 markers being placed. Right, so construction's failing for those reals. But the Bayes density theorem tells us that this immediately gives us this set as measure 0. Why is that? So we know that for the reals in this set, for almost all of them, the limit density must be 1. Right? But there can't be a single real in this set for which the limit density is 1, because when you place the E marker, the module satisfies the requirement for a fixed proportion of the strings above. So there are reals that are not in this outcome. Okay, so this potentially problematic outcome we can always just ignore. It's always going to be measure 0. Which simplifies things whenever you're using the framework. Okay, and then the last possibility is that there are only finite many permanently armed markers placed on initial segments of X. So these are the X which correspond to like permanently reserved measure at some point, right? So yeah, so these we have to care about, but they're generally fairly easy to care about. I mean, if it's just the permanently reserved measure. So if you think in terms of the example, if the E markers are reserving measure at most 2 to the minus E, and we only work with the E markers greater than K, then in total we'll reserve measure at most 2 to the minus K. Okay, so, and then so that gives a proof, in particular that, so if every sufficiently random bounds a one generic, which is quite easy to see anyway, and if you analyze it, it's obvious that 2 randomness arises. Okay, so let's look at some more properties. So I talked about the coupling property a little bit at the start of the talk, but there's quite a lot more detail. So, right, so a degree A satisfies the coupling property. It can be non-trivially coupled up to all degrees above. And the background here is maybe the strongest result, or one of the strongest results. So all A and R degrees satisfy the coupling property. Okay, so A and R means that for every function f, WTT reducible to the halting problem, U computer function not dominated by f. So it's kind of like, in some sense, it's like a generalization of being non-GL2. And the degrees that satisfy coupling, they're upwards closed. So this really says, as long as you're reasonably high up in the structure, you will satisfy coupling. Also, all PA degrees satisfy coupling and so on. Okay. Right, so then what happens when you think in terms of measure? So this was the first result I mentioned. So most degrees don't satisfy the coupling property. And in fact, you get a much stronger result than that. So in fact, all 2 random degrees have a strong minimal cover. Okay, so we say B is a strong minimal cover for A if the degree is strictly below B, and precisely the degrees below and including A. Okay, so maybe I'll draw a picture of that to be clearer. So if B is here, this is the stuff below B, this is the stuff below A. There's nothing below B, strictly below B, except the stuff below A. So that makes it clear then. So if B is a strong minimal cover A, then it kind of witnesses the fact that A doesn't satisfy the coupling property. Okay, because there's no way A can be coupled up to B. Okay. Right, but then we've got this heuristic principle, right? We want that whenever a natural property holds for all sufficiently randoms, it holds for all non-zeros below. So this better be true, and it is. So in fact, all degrees below any 2 random degree have a strong minimal cover. Note that none of them are a strong minimal cover, because they all satisfy the join property. So you've got this measure 1 set of stuff, all of which has a strong minimal cover, none of which is a strong minimal cover. So then, that's the measure side of things. Let's look at the category side. Yeah, so this, I mentioned this briefly. So this was given by Jokush. So in fact, this one goes the opposite way. So this is the first property, which goes differently when you think in terms of measure, when you think in terms of category. Okay? So thinking in terms of category, the typical degree does satisfy coupling. So 2 genericities level required, and that's sharp, so you can have 1 generics, which have a strong minimal cover. Okay, so there's the summary of where we are so far. Okay, so consider the 4 different properties so far. So the first 2 is exactly the same, whether you think in terms of measure or category. Join was almost exactly the same, but the levels require a bit different. And then coupling, for the first time, you've got it goes differently. So yeah, so now we have an actual property that goes differently when we think in terms of measure, when we think in terms of category. But we still don't have a natural definable property which distinguishes the theories of the lower cone. Okay, so we want a sentence which belongs to the theory of the degrees less than or equal to A whenever A is sufficiently random, and doesn't belong to the theory of degrees less than or equal to B when B is sufficiently generic. That's the next thing we would ask for. So with that in mind, let's consider the property of being a minimal cover. Okay, so right, so the most famous results are which degrees are a minimal cover. I guess the most famous result is that there's a cone of minimal covers, right? Basically just because the corresponding Gale-Stewart game is determined. So you either have to have a cone of things which aren't minimal covers or a cone of things which are minimal covers, and the first is impossible. Okay, and then so the category side of things here was completely answered by Kumabi. So he showed for every n greater equal to 2, every n generic, well, it's not only a minimal cover, in fact, it's a minimal cover of an n generic. Okay, so that's more than you need. So most of them are minimal covers. But then the measure side of things seems to be tricky. Right? So we've tried to answer this because we think it might give a difference between the theories of the lower cone. So maybe, I don't know, maybe this is a property where the level required is 3 randomness or something, so our methods won't suffice.
You're pointing at one generic.
Oh, sorry, I meant the next one here. The one generic, actually, I think the one generic, that's probably, I think my student can answer that. Okay. Right, so I guess this is the kind of the simplest candidate we have at the moment for separating the theories of low-code. Okay, so let's just briefly consider a couple more properties then. So being the top of a diamond, so the definition is kind of obvious, right? So at the top of the diamond, you have B and C, which simultaneously cup up to A and cap down to 0. And the result here is, okay, so if you're too random, then you are on top of a diamond. And again, the heuristic principle holds, in fact, all non-zero degrees below are too random are on top of the diamond. And I won't talk about the meat side of things, sorry, the category side of things here, because everything I say would be immediately eclipsed by what I'm about to say here. Okay, so this is the last property, the complementation property. So A satisfies the complementation property if all non-zero degrees below B below can be simultaneously cupped up and capped down. So the background here, whilst the 0 prime satisfies the complementation property, and from that you can always easily get that everything above 0 prime satisfies the complementation property. And then this was extended by Noam, Antonio, and Richard Shaw. So in fact, all generalized high degrees satisfy the complementation property. That's by a non-uniform proof, something that's presumably still open if you can do it in a uniform way. Okay, and then the category side of things here is completely answered, well, basically completely answered by Kumabi. So all 2 generics satisfy the complementation property. So the obvious question then is 2 genericity necessary, or does 1 genericity suffice? But again, for the measure side of things, we just don't know. Okay, so that's an open question. So the summary of the properties considered so far, these are basically, the picture's fairly so complete. There were quite a few questions, the first one, but they don't here. But when it gets to this level, we're not really sure what's happening in the measure side of things. Okay, so to finish with, I just want to talk a little bit more about the theory of the lower cone. So I said a little bit about it, but now some more detail, okay? So, if the definable property we're considering actually only refers to the degrees below, then you're never really quantifying over sets, right? You're only ever quantifying over indices, really, okay? So that means all these sets, the satisfying class is actually arithmetically definable. So we do have arithmetical determinacy. So in this case, it really must be the case that all sufficiently random degrees satisfy the property, or all sufficiently random degrees don't. You don't have to worry about whether it's measurable or not. Okay. Cool. But then there are only counting many sentences, right? So we can list them, phi 0, phi 1, so on. And for each of those, then you can take some set. For each phi I, you can take some set AI, such as being random relative to AI or being generic relative to AI, suffices to decide whether or not phi I is in the theory of your lower cone. And then, okay, there are only counting many of them, so we can take A above all of those. So there's certainly some oracle A, such that being random relative to A or being generic relative to A suffices to decide the theory of your lower cone. In fact, it's obvious that being arithmetically random will suffice, and being fully generic, so being n generic for all n will suffice. Right? So the point is that all sufficiently randoms have the same theory of the lower cone. So we note that this way. And all sufficiently generics have the same theory of the lower cone. So note that this way. So then there are 2 sort of natural questions which pop up. So first of all, how much genericity or randomness is needed to get to that common theory? So your guess is it would be just full genericity is required. That's the first question. So, okay, so more specifically, is there an n such that for every n generic, the theory is already the common theory? Or is there an n such that for every n random, the theory is already the common theory for randoms? And then, are those 2 common theories the same? Okay, so Shaw has shown that both of those get negative responses, the kind of way you would expect. So in fact, he has a sentence which is satisfied for all 3 randoms, and the negation is satisfied for all 3 generics. So the natural question then is, okay, can we find a natural example of a property of that kind? Okay, so I'm going to finish now. I'm very early, but anyway, yeah, I'll finish. Thanks.
Questions?
Yeah.
Tell us some more about the beefed up framework. How does that work?
The more complicated, well, okay. The reason I avoided doing that, because that one gets messy. So it's kind of, okay. Have you read the Jeff Paris paper, the measure that we found minimal to 0? Because it's kind of the same sort of flavor as that. Basically, rather than just having markers, you have like markers and sub-markers, and you have to kind of keep on moving the sub-markers and restarting again, and so you have, kind of works at 2 levels. I think, okay, describe it in detail would be difficult. Okay.
These questions look quite difficult. Is there a strategy?
Well, some of the questions I asked, I have no reason to believe are difficult, and some of them I have reason to believe are difficult. So, okay, so...
I simply these ones on the slide.
Oh, well, they're not.
Oh, right. Oh, sorry.
Yeah.
So is it difficult?
No, I think it's just standard. I mean, he hasn't actually written this paper, so I haven't been able to read the proof yet. But I think it's just the sort of basic coding techniques. You kind of somehow you code in the fact sufficiently randoms. You code in the fact that I bound a 3 random, and that can't be satisfied by generics or that kind of thing.
So if all you know, under enough, if you assume that all projective sets are Lebesgue measurable and all projective sets have the Baire property, then there's a typical theory of a degree, not just the lower cone.
Right.
So you've seen some distinctions. It is, I don't know. Can you ask similar questions about the? I guess the second question. So the question of whether the common theories would be the same is.
So we've already got
answered by
difference
the
there. So
results
we've got
already
the coupling property
coupling
goes a
property,
different way.
yeah.
So that's the right. That's really the only one where we have. That's the only difference we have so
And
far.
how much genericity or randomness then would you need?
So that is 2 randomness. So in both cases, in one random, 1 generic, they have some do, some don't. I guess. Yeah. So it's 2 randomness, but they're definitely different.
Is one randomness and one genericity?
Do I have a difference with them? No,
Yeah.
I guess not. No.
Or is so let's see. So you don't know that one generic is sufficient to establish the full theory, or one random.
Well, no. So you know that. So there will be 1 generic. So even if you just the lower cone, their theory is different than the 2 generics. There'll be 2 generics. Their theory, the lower cone, was different than the 3 generics. So that works for all n.
Yeah.
All going all the way up, right? So you definitely need full genericity in order before you've got even just with the lower cone that you have.
Oh, okay. All right. Okay.
So Noel had a question.
Yeah, so, okay, maybe that's obvious, no, I was trying to explain. Is there any hope that instead of n, you try alpha, you try to add even more randomness, right? N random is not the end of the story, right? Or is this completely
Well,
known
the
that-
problem is here you already got to a common theory once you're arithmetically random.
Okay,
So
right, okay.
maybe if you want to start expanding to different languages, in which you've got I don't know, L omega, 1 omega, I don't know.
I guess that's what I'm getting at for the common theory of the typical degree. Forget about the lower cone. Assuming enough sets are Lebesgue measurable and
One number.
Yeah.
property of Baire. How much genericity do you need?
But I mean, stuff about the lower cone is still part of the theory in the general structure, right? I should say for all p below the top degree. So if I have a difference there, then
Yeah.
that gives a difference.
No, okay, that's for difference between random and generic, but
Yeah.
but how random does a real have to be to make sure
Oh, I
that
see, I see, yeah, okay,
randomness
okay.
theory
Then I don't know. Okay.
is
Yeah.
the typical
Right.
theory is typical,
I pass, I'm not
and
sure.
how generic does a generic degree have to be?
Yeah, not sure. Yeah.
Actually, I have a question. You talked about some notions intermediate between 1 and 2 randomness.
Yeah.
Did you look at week 2 genericity at all?
No.
Okay.
Week 2 generosity. Yeah, well, for some of the, I didn't mention it there. I guess, yeah, we did for some of the stuff, but that's week 2 generosity is enough that you will satisfy the coupling property, for
Okay.
example. So there are some things you can do for that.
Okay. Are there any other questions lurking? Well, if not, let's thank the speaker and reconvene in 14 minutes.